Hello, AI enthusiasts. Welcome to a new deep dive. Building on our previous talk about ensemble learning, where we discovered how combining many imperfect guesses like a crowd estimating jelly beans in a jar converges closer to the truth than any single guess, we now explore bagging. Most videos on bagging show you the complex statistical equations, but skip the structural intuition. In this video, we want to show something different: the way parallel opinion polls create a rock-solid foundation for prediction, even when individual models are shaky. In the world of machine learning, bagging stands for Bootstrap Aggregating. Think of it like running 5 independent phone polls simultaneously. If you only run one poll, you might accidentally call a group of people who all share the same bias, leading to a noisy and inaccurate result. But by running these polls side by side, we ensure that no single error can ruin our final answer. Just as each poll in bagging is like running a separate jelly bean counting contest with a different random crowd, these booths work in isolation to provide their own unique perspective. To make these polls truly independent, we give each booth a different random sample of voters from our master list. Imagine rolling a dice to decide which citizens each booth gets to interview. Some voters might be called by multiple booths, while others might not be called at all. This randomness is the secret sauce. By training each model on a slightly different subset of the full data, we force them to see the problem from different angles, preventing them from all making the exact same mistake. Why go through all this trouble? Because individual models are often hypersensitive to their training data, a problem we call high variance. In our polling analogy, if one booth happens to call a very vocal but small minority, its prediction will be wildly off. It is like a weather vane that spins at every tiny gust of wind. If we relied on just this one booth, our final prediction would be unstable and prone to error every time the input data changed even slightly. This is where the aggregating part of bagging happens. Once every booth has finished its independent poll, we collect all their results and calculate the average. Think of it as a central committee that ignores the outliers and listens to the consensus. While one booth might predict a value that is too high and another predicts one that is too low, these errors tend to cancel each other out when they are combined. The result is a much more stable and reliable estimate. When we look at the data visually, the difference is striking. The jagged teal line represents the noisy guess of a single polling booth, reacting too strongly to every local fluctuation. In contrast, the smooth blue line represents our bagged average. By spreading the work across multiple random samples, we have successfully reduced the variance. It is the mathematical equivalent of taking a deep breath and looking at the big picture, rather than overreacting to every single data point we encounter. Bagging is also incredibly robust against outliers. If one polling booth happens to capture a group of extreme voters who do not represent the majority, that booth's result will be an outlier. In a single model system, this would be a disaster. But in our parallel polling setup, that one extreme result is diluted by the 4 other booths that saw more typical data. It is like a safety net. The collective wisdom of the group protects the final output from being dragged down by a single bad sample. While you can use bagging with many algorithms, it works best with models that are naturally prone to high variance, like decision trees. A single decision tree is like a very specific, detailed poll that can easily get lost in the weeds of specific data points. By creating a forest of these trees, each trained on a random sample, we create what is known as a random forest. Each tree makes its own decision, and we take the majority vote, or average, to find the most likely truth. One of the greatest practical strengths of bagging is that it is embarrassingly parallel. Since each polling booth operates independently, they do not need to wait for each other to finish. You can run 5, 50, or 500 polls at the exact same time across different computer processors. This is like having 5 separate calling centers working on a survey simultaneously instead of one person making every single call. This efficiency makes bagging a go-to technique for massive datasets where speed and stability are both required. To recap, bagging is the art of reducing variance by averaging the opinions of multiple independent models. By giving each model a unique random sample of data, we ensure they learn different patterns and make different errors. Like 5 parallel poles converging on a single accurate prediction, bagging transforms a collection of unstable learners into a robust, reliable predictor. It is a simple yet profound reminder that in machine learning, just as in a democracy, the consensus of a diverse crowd is often much smarter than any single voice. Now that you have seen how bagging stabilizes your models, you are ready to tackle even more complex ensemble methods. If you found this visual journey through the world of parallel poles helpful, hit the like button and subscribe to join our community of data explorers. We have many more deep dives coming your way, from the intricacies of boosting to the mysteries of neural networks. Keep questioning, keep learning, and we will see you in the next deep dive into the heart of artificial intelligence. Subscribe for more insights on how bagging reduces variance in your models.